It is my great honor having this opportunity to pay my great respect to Professor Bonse. I think his best work is on X-ray interferometry. This idea is so smart and insightful, making creative use of X-ray wave interference for major biomedical applications. His spirit likes X-rays, radiating our field and inspiring generations of researchers in the past, now, and years to come. I met him when I just got my PhD degree. To me, he is a giant, a hero, and a role model. I certainly admire his groundbreaking contributions to BH interferometer, X-ray micro-CT, phase contrast micro-CT, and equally important to the SPIE community, by establishing our SPIE X-Ray Tomography Conference series. In my presentation, I would like to comment on the association between what he pioneered and what we are doing today through the lens of generative AI, since generative AI is a contemporary theme, and you may hear it many times, such as Year of Generative AI, etc. Here is the outline of my presentation to cover the three aspects in which Professor Bonse made distinguished marks: interferometric imaging, micro-CT, and the SPIE service, especially our SPIE CT conference series. Indeed, as you will see on the subsequent slides, both interferometric imaging and micro-CT are closely related to generative AI. AI, especially deep learning, methods were initially developed in the supervised mode where labels or ground truth are available. This machine learning mode has demonstrated amazing performance in classification or regression tasks, such as image recognition and image denoising. In the deep biomedical imaging field, when there are labeled big training datasets, we can train a deep network to map a low-quality image, such as a noisy CT image, to a high-quality counterpart, for example, a denoising CT image. Here is a figure in our review article on deep tomographic imaging, illustrating the supervised learning tasks for major medical imaging modalities. In contrast to supervised learning, generative AI represents a more advanced learning mode, which is closely related to unsupervised learning, semi- or weakly supervised learning, or self-learning. Often, supervised learning is performed for discriminative AI tasks, where we derive a decision boundary as shown here to judge if an input image is 0 or 1. On the other hand, generative AI is performed in a self-learning mode without any label to model a complicated data distribution. Once we have a model of a data distribution, we can sample this distribution to produce many plausible samples under the modeled data distribution. For example, we can generate many 0s and 1s. On this slide, a decision boundary is one-dimensional, while a modeled data distribution is two-dimensional. That is, generative AI has advantages of higher dimensionality over discriminative AI. There are many generative AI methods. An early milestone is the variational autoencoder. Then, generative adversary networks become dominating. Now, physics-inspired generative models have taken over, particularly those network models that are based on non-equilibrium dynamics and electrodynamics. Our latest review on physics-inspired generative models was just accepted by Annual Review Biomedical Engineering. Here is the arXiv version for your convenience. Two exemplary types of physics-inspired generative models are diffusion models and Poisson flow models. The Poisson flow models follow the principle of electrodynamics. The key idea can be illustrated on the left. Suppose that the data distribution is just one-dimensional, and this distribution can be viewed as a charge distribution. Then, we augment the data space to form a two-dimensional plane, where an electrical field can be easily computed. While the near field has distribution-dependent features, the far field is uniform on a big semicircle shown on the right. We can randomly sample the big circle and trace into the data space to generate a new data point under the original data distribution, serving the generative purpose. More important is the so-called conditional or condition generation. We can steer the generative process according to desirable constraints such as tomographic measurement and preferred image characteristics, such as the condition generation is nothing but tomographic image reconstruction. Interestingly, the idea behind the Poisson flow generative model is somehow similar to that behind our image unraveling work performed 2 decades ago. At that time, we wanted to unravel a convoluted colon into a linear display. To do so, we assume that positive charges are distributed along the colon central path. Then, resultant electrical force lines naturally define curved cross-sections that are never in conflict. Clearly, our method only utilizes the near field structure and has nothing to do with the far field. This slide shows some realistic bedroom pictures generated by the generic Poisson flow model. They show an impressive generative capability of the AI model. Although the quality of the images produced by the Poisson flow model is excellent, when we track the electrical force line back to the data domain, the number of steps involved are typically hundreds or even thousands. Inspired by the convergency model designed for the diffusion model, we recently combined the Poisson flow model and the consistency model to form our Poisson flow consistency model that can take only one step to obtain the final result. Here's an example in the case of low-dose CT denoising. We obtained the denoising outcome in one step, which looks very comparable to that obtained in about 100 steps using the generic Poisson flow model. In principle, conditioned generative AI methods can be used to solve all inverse problems, as long as high-quality training data is available or can be realistically simulated, even without any labels. In other words, contemporary generative AI methods give us a great opportunity to upgrade attenuation, phase contrast, and dark field tomographic image quality. In our lab, we have a grading-based micro-CT system and can produce tri-contrast images as shown here. In this conference, I learned the new idea called single absorption grading. I believe generative AI can help in all these situations. Different from the Poisson flow generative model that is based on electrodynamics, the diffusion model is based on non-equilibrium dynamics. Simply speaking, the diffusion model, such as the DDPM, keeps adding small Gaussian noise and reducing an input image, and eventually produce a featureless Gaussian random field. This forward process can then be reverted to go from a realization of the random Gaussian field to a realistic image under the distribution of training data. The conditional inverse process of this type can be used for image grading-based imaging tasks, such as denoising, deblurring, and artifact suppression. We have just discussed the linkage between generative AI and interferometric imaging. Next, let us see the potential of generative AI in micro-CT that Professor Bonse and others pioneered. In particular, my group has been pushing the idea of clinical micro-CT for more than a decade. Clinical micro-CT is to produce in vivo micro-CT images of a patient instead of a small animal. The image resolution of medical CT has been quite stable and currently is about 200 Higher resolution is highly desirable, especially for inner ear imaging, artery plaque stratification, and other tasks. For cochlear implantation, a 50 resolution micro-CT will help the surgeon greatly. Another example is vulnerable plaque characterization. Histology studies suggest that 65 fibrous cap thickness is a key biomarker of plaque vulnerability. This resolution requirement is far beyond the capability of current clinical CT and MRI. To enable clinical micro-CT, we recently proposed a robotic arm-based micro-CT system. We use robotic arms to drive a novel microfocus X-ray tube with 4x more flux than the prior art, and a photon counting detector with fine detector elements and spectral sensitivity to ensure 50 spatial resolution. Furthermore, we use interior tomography for ROI imaging to minimize the radiation dose to a patient to a level compared to that of a regular head CT scan. However, this new platform faces new challenges. Primarily, 50 resolution requires an accurate imaging geometry, which can be compromised by robotic coordination errors and involuntary patient motion. Furthermore, the lateral truncation of the projection data also add another layer of difficulty. Our group is developing a data-driven method for view-based calibration of imaging geometry, even in the case of biliteral data truncation. This computational mechanism is critical to make sure we have accurate imaging geometry and hence ultra-high image resolution of clinical micro-CT. In this example, the original image reconstruction assuming nominal imaging geometry shows double edges and blurry as indicated by the red arrows. Our data-driven geometric calibration method can clarify the compromised structural details. Like what I mentioned in the first part of this talk, for clinical micro-CT, a modern generative AI model can also help significantly in various settings, such as limited angle CT, sparse view CT, and interior tomography. On the right, we see an illustration in my paper entitled Cone Beam Reconstruction of Plate-like Specimens, published in 1992. This is exactly the laminography as reported in several talks in this meeting. Since the acquired dataset for laminography is not sufficient for analytic exact reconstruction, generative AI can offer comprehensive prior knowledge to maximize the image quality. Atsushi just mentioned the idea of phase contrast tomography using the BH interferometer. I think generative AI can help that similarly. Finally, let us review the SPIE Conference series established by Professor Bonse and others. This has pushed the development of the field of X-ray tomography and generated a large effect on international collaboration. Recently, I did a Scopus search with the Boolean formula, X-ray and tomograph asterisk and conf SPIE, in the title, abstract and keyword fields. This search retrieved about 3K documents as evidence showing the establishment of our community. This field is highly interdisciplinary, covering materials, physics, medicine, computer science, engineering, and mathematics. The researchers are from the whole globe. The USA made the largest contribution, followed by Germany, Japan, and China. Among the SPIE papers we retrieved, Felix, Bert, and I published 49 papers each person, who are the most productive researchers in terms of the number of papers. When I first attended this conference many years ago, China had opened her door for international collaboration. At that time, many scholars in China were not good at English, and their submissions were not written smoothly. Professor Bonse asked me to offer help. The work turned out to be very pleasant and rewarding. He encouraged me much, and I appreciate the opportunities he gave me. Today, the language barrier is diminishing thanks to large language models which use generative AI methods. For example, I asked ChatGPT in English what Professor Bonse's main contributions are. The answer is on the top left, based on which I made the outline of this presentation. Then I asked ChatGPT to translate it into German, France, and other languages in seconds. Interestingly, the Chinese and Korean translations are the most compact. I assumed that Professor Bonse was in this room during my presentation. I have tried to update him on the latest progress based on his pioneering research and international leadership. I will keep doing my best, following his footsteps towards better healthcare and a brighter tomorrow. Thank you!